All right, everyone, welcome back to part 2 of sugars. Let's begin. All right, so we learned that sugars pretty much exist in both a cyclic and a linear form. Most of the time, they exist in this cyclic form. So we can take we can take advantage of the fact that there is an equilibrium, even though most of the time it is in the cyclic form, and we can actually react it with certain reactions that we've seen before, such as NaBH4. And modify the actual sugar. So in aldoses, we can make the ends, so the aldehyde ends, equivalent to the other end. And this produces an alditol. And basically we just use NaBH4. So this is just a genuine reduction. And this is an acyclic alcohol. So please remember this is acyclic. This is going to exist only in the linear form now because it cannot cyclize, it cannot form that hemiacetal. All right, so alditols actually sound familiar because we use them as sweeteners in a lot of different products. So, for example, if you gum, there's a lot of alditols, like xylitol is, for example, one type of alcohol that we have in our different types of candies and whatever. Anyways, besides the point. So the second reaction, we can produce what's called an alderic acid, and basically this is just a carboxylic acid at both ends. So we take this aldehyde end and we turn to carboxylic acid. Here we're taking aldehyde and we're just reducing it into an OH. Here we're just making it, we're oxidizing it and making it a carboxylic acid. Okay, let's continue. All right, so remember chirality. So in sugars, chirality is actually relatively straightforward to tell. It's always best to do it through the Fisher projection. So drawing the Fisher projection is the first thing you should do. After NaBH4 is applied to the sugar, right, we can make this molecule symmetrical. Possibly, it depends on the sugar. If I start with something like D-allose and I apply NaBH4, I'm going to reduce the aldehyde, and now I have a possibility of symmetry. If it's symmetrical, down the center, so I basically draw this line cutting through, and you basically fold it like a book. So as you can see, these two hydroxyls are both on the right, and these two are both on the right. So this is actually symmetrical, and therefore it's achiral. All right? Let's do the same with D-galactose. So right now there's no chirality possible because we have an aldehyde here and we don't have an aldehyde here. Or we have a hydroxyl here, we don't have a hydroxyl here. But after applying NaBH4, we can actually get this achiral compound because if we cut down the middle and then we fold like a book, this OH and this OH are the same side, and then this OH and this OH are on the same side. So I think that's the easiest way to think about it. So remember, if it's optically inactive, it means that it's achiral. If it's optically active, it means that it's chiral. So this was actually very useful back in the day to identify unknown sugars. You'd apply this reaction, then you would see if it rotates light or not, and that would help you distinguish between what type of sugar it could be. Okay, so what about ketosis? So yeah, we can apply NaBH4 on ketosis, and we make this new stereocenter at the carbonyl carbon. So this is the carbonyl carbon, so we can make a new stereocenter where we have the OH on the right or the OH on the left. So here we make disorbitol, and here we make dimannitol, as you can see. Disorbitol is going to be, if we cut down the middle, right, let's say if I drew my H here as well, you can say that this is chiral. However, with dimannitol, dimannitol is also chiral. No, however, dimannitol is chiral, okay? Hopefully that makes sense. Let's continue. So we could do what's called the Wohl degradation. It's another reaction that we can do. So we can basically remove the top rung of the Fisher projection for aldoses. So before we even start this reaction, what we're going to do is we're going to take this rung, let's say it's a ladder, right? That's what we call a rung. And we pretty much remove it. So now this is the top rung. We pretty much get rid of it. So how do we do this? Well, we're going to first create this beautiful oxime. Okay? And so please review the mechanism of oxime from my previous video if you don't remember. It's not really necessary, but it's always nice to know. And then you're going to pretty much just use some acid, and we're going to dehydrate this oxime and create this nitrile. and then you're going to break this nitrile with some base. That's pretty much it. So if you see these three reactions in order like that, remember, Wohl degradation, all we're going to do is we're going to basically destroy this first rung and shrink the sugar by 1 carbon. Hopefully that makes sense. Go to the first practice problem. This relates with chirality. After we reduce with NaBH4, which of the following aldoses are going to be achiral? So take some time and think about which one is going to be achiral. So apply the trick that I used. Okay, so here's the answer. So how did I do this? Pretty much what you would do is you would go through each sugar. So I'm going to go through just the ones that are achiral. I'm going to cut down the middle, and you can see that if I fold like a book, it's going to fold in on itself. So I didn't actually reduce them here, so this is just the same sugars, but I'm asking which one after applying NaBH4 is going to be achiral. So all of these that are drawn here are chiral, right? But once I apply NaBH4, then they're going to be achiral. So OH is here on the same side. That's always easiest thing to look for. If they're all on the same side, then you're going to know that it's achiral. So that's how you get those three. And then to get galactose, if I cut down the middle, once again, you can see 1, 2, and then 1, 2. And then xylose, if I cut down the middle, 1, 2. Okay? All right, hopefully that is clear. Let's do a second practice problem. So remember, Wohl degradation, it's nothing that you haven't learned before. What do I do here? Think about it. Draw the Fisher projection. Remove the top rung of the ladder. What will you get? So that's my answer. Okay? And so how can I actually compare that I did it right? Well, once again, this is going to be this carbon. Carbon 1. All right? This is 2, 3, 4, 5, 6. So 6 is not touched at this at all. So just going backwards, 5 is not touched, 4, 3, so 2 is what we got rid of. All right, so we got rid of 2. So pretty much what all you're going to look at is you're going to look at this OH and this OH, and then this one's always going to be there. So I think for Wohl degradation, you can either work forwards or backwards. I think it's probably best to work backwards here. So number backwards. I always said number from the most oxidized, but if you're removing the second rung, right, or the first rung really, but you're removing the second carbon, you might be a little misled at first as to looking at the Haworth projection. But it's up to you. So as long as you get it right, that's the best way to do it. All right, let's talk about what a glycoside is. So pretty much it's an acetal. So remember, we always form these hemiacetals, but in real life, right, and in your body, for example, glycogen has these glycosidic bonds where we have these long polymers of glucose. And pretty much it's just an acetal that exists. So we have this OR, and then this R could be another sugar. And you can actually go between these formations through these sorts of reactants, right? But pretty much we're going to be mainly looking at hydrolysis rather than actual formation. But hydrolysis is going to be performed using acid. You can also form it using acid and an alcohol, but it's not really what we're interested in too much, right? But this is so if you have this sort of sugar here, and you have this mixture of anomers because of that squiggly line, well, you're going to form two types of sugars after applying this reagent. Okay, after applying methanol and acid, you're going to form one where it's up and one where it's down. So keep that in mind. So with hydrolysis, you can also hydrolyze these. And once again, so going backwards, right? Remember, we formed this mixture. We had this mixture, and then we formed up, down. Well, if we go backwards, we're going to form a mixture again. Keep that in mind. There's no way to tell if it's going to be alpha or beta. All right, so in theory, how would we form a disaccharide? Well, what is a disaccharide to begin with? It's a glycoside where the R group is another sugar, or really a hydroxyl from another sugar. Okay, so in this case, we're going to be coupling this anomeric hydroxyl, right? Anomeric carbon hydroxyl with, and you're going to basically make this H into an R, and the R is going to be another molecule of glucose in this particular example. And this is pretty much, you're going to form this acetal with acid. In theory, once again, this is why it's, in reality, it's going to form a lot of side reactions, but in theory, you're going to form this glycosidic bond, and it's going to form a new acetal. And the acetal is a 1,4 glycosidic linkage. Why is it alpha? Well, this is pointing up, and this is pointing down. So it's based on the anomeric, the sugar with the anomeric carbon, that's part of the glycosidic bond. That's the one that you use to tell whether the linkage is alpha or beta. Okay, and so because this one's pointing down, this one's pointing up, we know that's alpha, and then the 1,4 is basically the carbons, so 1 to 4. So just to review, we can create a disaccharide, in theory, using acid, and this disaccharide, we can call this linkage. It's going to be alpha or beta based on the anomeric carbon, and the numbers in it are going to correspond to the actual glycosidic linkage carbons. So hopefully that makes sense. Let's continue. In theory, we can also hydrolyze these in aqueous acid. Or in reality, in your body, what's going to happen is you're going to have an enzyme that's going to come in and break it, right? It's pretty cool. Like glycogen phosphorylase is going to do that, but that's a whole nother video, and that's a whole nother class. So in this case, we have this beta 1,4 glycosidic bond. Okay, so 1,4, and we can see that it's beta because this is pointing up and it's pointing up. And we can use acid to break this, and this is going to give a mix of stereoisomers. So we had a mix here that doesn't change here, and then this hydroxyl that was part of the actual acetal is also going to become a mix of stereoisomers because we have no way of controlling it in this just plain acid. Okay, so what is the way that we're actually going to be doing this? Actually, rather than just throwing methanol and acid and praying, right? We're going to do this in 2 phases. First phase is what's called exhaustive methylation. The second phase is aqueous hydrolysis. Why is this? Well, first we are going to methylate, meaning on every single available OH, we methylate. So I'm going to get 1, 2, 3, 4, 5 methyls added. So now this cannot interconvert. So what do I mean by that? Well, I cannot convert between the linear or the cyclized form. It's just the cyclized form, and I have it written here. Why? Because I get rid of that OH. And then after doing aqueous hydrolysis, right, we use aqueous acid, we're just going to only affect this methoxy group, the one that's on the anomeric carbon. And that's what's beautiful about this. It's only going to affect that one. Everything else is still going to remain methylated. So it's actually selective hydrolysis. This is what's called. And you get both the alpha and the beta. There's no way to control for it. So basically you can write a squiggly line out here. So keep in mind, and this point, let's draw the fissure. Okay, so I pasted this fissure projection model in because it's just easier than drawing it myself. So what I'm trying to draw is the fissure from this glucose after we did the selective hydrolysis. Okay, so the most important part here is that I want you to understand is that this carbon 5, is going to now be an OH. Okay, by now be I mean before we couldn't draw in the linear form because it's an acetal, right? You would have to break that acetal, but now it's a hemiacetal, so it cyclizes because it's a hemiacetal. But every other CH2OH. You know what? That's going to be a little misleading. Let's do CH2OH. So now we have an aldehyde that actually exists because of this cyclic, right, nature. 3, 4, 5, and 6. So if this is 1, this is 2, this is 3, this is 4, this is 5, this is 4, this is 5, and this is 6. So keep in mind that this carbon, on carbon 5, you're going to have that OH. But on every other carbon, so 2, 3, and 4, it's going to be methylated. All right. So once again, if you have this hemiacetal, after you did the aqueous hydrolysis, after methylating it, your carbon number 5, or the one right before the non-chiral carbon, one right before it, that's chiral, should have an OH. That's how you can actually tell. It's the easiest way to tell. You should have an OH because there's an OH here. Okay? So it can cyclize. So pretty much electrons would collapse here and kick back, and that's your 5. So hopefully that makes sense. So and now just drawing the Fisher projection together. So it's a little hard to tell, but this is going to be down. Carbon 3, it's going to be up. Carbon 4, it's going to be down. Notice how everything here is an OCH3. This should also be an OCH3. Everything here is an OCH3 except this and except aldehyde. Please keep that in mind. Okay, so here is a live example of that it being put into action. So we start with this disaccharide here. And what we do is we methylate it. So you can see every single hydroxyl is methylated. And we're going to use the selective hydrolysis, so it only affects the C1 carbon. So this is the C1 carbon. After hydrolyzing it, we're going to get 2 types of monomers. So this bond here, it's not very clearly drawn, but as you can see, this right here is pointing down. It's below the plane. And this is pointing up. So what type of bond is this? Well, if I count, this is 1, this is 2, this is 3, this is 4, and this is 1. So this is a alpha on 4 linkage. After breaking this linkage, I'm going to get, this is going to be alpha, and as you can see it is. And then this one does not necessarily have to be alpha, but you're still going to get that OH because that's the C1 carbon. So it's going to perform the selective hydrolysis at both monomers. So both monomers are going to get that hydrolysis at that C1. We're going to form OHs on both. So on the monomer that had the anomeric carbon part of the glycoside, so this one, you're going to form the alpha. So you would draw the alpha. And then on the monomer that didn't have the anomeric carbon forming glycoside, you would draw just with the squiggly line. So please keep that in mind. Okay, well, that is the end of this video. So thank you so much for watching, and I'll catch you in part 3.